Transfer matrices. At the start of this lecture, we'll start off just by trying to give you an intuitive feel with some neat illustrations of what the transfer matrix method is and how it works. Then we'll dive into the math and how to calculate transfer matrices, and in the end, we'll show it all doesn't work anyway. Well, it sort of does. We can fix it. So we want to understand all of this, though. So let's dive right into this. Concept of transfer matrices. So here's our ordinary illustration of what the transfer matrix method is simulating. Infinite slabs of different material. They're not infinite in the z direction, they're finite in the z direction. But we would like to somehow model or simulate transmission through this stack of layers. And I'm only showing 4 layers here, but it extends to any number of layers. So the first thing we'll need is, what does the field look like at that input face? And so we'll call that E sub naught, H sub naught, the 0 meaning the very beginning of this device. So we'll move that off to the side, just to remember that it's there. And we would like to calculate the field at the next interface, at that plane between layer 1 and layer 2. How on earth do we do that? Well, what we'll do is we will calculate a transfer matrix that essentially simulates propagation through that layer, accounts for whatever scattering happens at the interfaces of either side of layer 1, and we arrive at the fields at that next interface, which is right between layer 1 and layer 2. So the transfer matrix simply lets us write the fields at that input face being pre-multiplied by our transfer matrix, and then we get the fields at that next interface. And this is going to repeat. At this point, we know the field at the interface between layer 1 and layer 2. We now like to know what the field is between layer 2 and layer 3, so we calculate the transfer matrix associated with layer 2. And by the way, that's what the superscript up here is indicating. That's which layer the transfer matrix is associated with. Once we know that, now we can go ahead and calculate the field between layer 2 and layer 3. So that field is known. Then we calculate the transfer matrix associated with layer 3. Given that, we can calculate the field at the interface between layer 3 and layer 4. That field is known. We then calculate the transfer matrix through layer 4 and use that to calculate the fields at the output face of this device. And we're done. We now have the field at the output face. Now, if we multiply all of these transfer matrices together, so you have the transfer matrix of layer 1, layer 2, layer 3, layer 4, notice the order that they're being multiplied. So 1 at the far right, then 2, then 3, then 4. If we multiply just the transfer matrices together, we get what's called the global transfer matrix. And the global transfer matrix directly relates the fields at the input face to the fields at the output face. So the way the transfer matrix method would work is that we calculate one transfer matrix at a time, multiply them together until we get a global transfer matrix, and then we can solve our problem relating the fields on the outside of the device. Let's think about the wave vector components inside of our stack of layers and what's going on there. The first thing we'll need to do is to calculate the wave vector components. Well, so we have an incoming wave in the incident region, which has a wave vector k ints. And given its angle of incidence theta and also its angle phi off of the x-axis, we can calculate the x and y components of that incident wave vector. And here's our equations. So it's essentially a spherical to Cartesian coordinate conversion here, but we also have the magnitude of the wave vector built in here. Now here's the interesting thing, and we'll get more into it in the next slide. Whatever these x and y components are of the incoming wave vector, those x and y components are constant throughout our entire device and even into the transmission region. They never change. it's only ever the z component that changes, and we would calculate the z component from the dispersion relation. So the z component changes in each layer. X and Y components are the same everywhere. Let's look at this in a bit more detail. So now we're looking at a little bit uglier picture of a stack of layers. We're looking at it from the side view, and here comes a wave, k ints. And we've calculated the x and z components. The y component is 0 in this case because we're looking at it from the side. Okay, so we have our incident wave vector. It has a tangential component, kx, and it has a z component. And if we wanted to, we could calculate kz from our x component. Let's think about the reflected wave. Every single wave vector component has to have that same x component of the wave vector. So kx will be the same everywhere. So for convenience, I'll just copy it over here. The z component comes from the dispersion relation. Well, since it's in the same medium as the incident wave, we really get the same kz. The difference is there's a minus sign here because the wave is going in the minus direction. And if we combine these two components, we get the overall reflected wave vector. Now let's look inside this stack of layers. Well, in the first layer, the wave vector component has to have this as the x component. That's continuous throughout the entire device. But the z component is calculated from the dispersion relation. We're in a different medium now. It has refractive index N1 instead of air. So we get a different z component, and if we combine these x and z components, we get our k1 wave vector in medium 1. If we move on to medium 2, again, it has to have that same x component of the wave vector. We get the z component from the dispersion relation. And of course, if we tie these two together, we calculate the wave vector in medium 2. Finally, in medium 3, it has the same x component. We calculate the z component from the dispersion relation. We tie these components together, and we get the wave vector in the third medium. And the very last thing, in the transmission region, it has to have that same k sub x. We calculate the z component from the dispersion relation. We tie the two together, and we get the wave vector in the transmission region. Now, this discussion is not talking about how much of the waves reflect off of each interface. We need the simulation for that. We're simply talking about the directions of the wave vectors. And the big conclusion is that the transverse component, and in this case x and y directions, whatever that is for the incoming wave, it's the same throughout the entire stack of layers and even into the transmission region. It's only ever the z component that changes, and that comes from the dispersion relation. Now let's move on to calculating the transfer matrices. This will get a bit more mathematical. Let's look at another side view of layer sub I, buried in the middle of a whole bunch of other layers. And to the left and to the right, we have other layers. So to the left is layer I minus 1, and to the right is layer I plus 1. This layer I has thickness L sub I, and so each layer would have its own thickness L, and we would just describe which layer with the subscript. Now, within this layer, it's going to have its own little coordinate system, and it's normalized. So we have the prime, but we'll write it as z sub I. The I is to remember this is the z coordinate in the I layer, which starts at 0 at the left interface and goes all the way up to L sub I. Now, within the layer, remember we wrote all of our fields into a single column vector that we called psi. So this contains all of the fields, and the subscript here reminds us which layer we're in. So this psi is a function of the local z coordinate, and that would change as the fields propagate from left to right through the layer. Also in this layer, we have our mode coefficients. The mode coefficients of the ith layer. Remember, these are really describing the amplitudes of the modes that are in this. That's what multiplies the eigenvector matrix and the exponential. So those mode coefficients are the amplitudes of the modes. At the very left side of the layer, I know I'm drawing it as a little gap here, but really this point is immediately on the interface, sort of in the limit as we approach there from the right-hand side. We will call that psi sub I at z equals 0. So that's the fields at the start of this layer. If we look at the fields at the other side of the layer, that's still psi sub I, but now our z is a k naught times Li. Remember, this Li is the thickness of this ith layer. And we have to multiply it by k naught because remember, this psi is expecting a normalized z. L is not a normalized parameter, but if we multiply by k naught, that's how we normalize our spatial coordinates. Anyway, this last term is the field at the end of the layer. Now, if we look in the previous layer to the left of layer sub I, well, that's just psi sub I minus 1. We're looking at the fields in the I minus 1 layer. And all the way at the far side of that layer, the z value is k naught times L sub I minus 1. So that's the length of the previous layer. In layer I sub I plus 1 to the right, the field immediately at the interface, but in the I plus 1 layer, is psi sub I plus 1 at its local coordinate z equal to 0. And of course, layer I minus 1 has its mode coefficients describing the amplitudes of the modes, and layer I plus 1 has its mode coefficients describing the amplitudes of the modes in that layer. So in the upper right is a quick summary of what we saw on the previous slide, and I'm writing the expression for the field in the ith layer. Remember, that was an E sub x, an E sub y, an H sub x, and an H sub y. And when we talked about the anatomy of this solution, we have our eigenvector matrix. That's the pictures of the modes. We have our exponential with our eigenvalue matrix here. This exponential is describing how those modes propagate. And then our mode coefficients, which are describing the amplitudes of the modes. So that's how we wrote our solution to that 4x4 matrix. Let's look at the boundary conditions at this first interface. So we really need to set this psi sub I minus 1 at k naught at L sub I minus 1 equal to psi sub I at z equals 0. So that's what we're doing. And now we borrow our general expression for the field, and we write these. Well, in the I minus 1 layer, it's the eigenvector matrix sub I minus 1 with our exponential, with our eigenvalue matrix sub I minus 1, and our mode coefficients sub I minus 1. So that is the field at the far right side of layer I minus 1. At the far left side of layer I, it's eigenvector matrix times the mode coefficients. Now we might say, where did that exponential go? Well, this is at z equals 0. And so if we set z equals 0 here, this exponential becomes the identity matrix. That's the matrix sort of equivalent of a 1. So it's not even there. Now let's do the same thing, but let's write our boundary conditions at that second interface between layer I and I plus 1. So we're setting these two psi's equal to each other. And that's what we're doing down here. Using our field expression for psi, we can write expressions for psi sub I at the far right-hand side of the layer. Eigenvector matrix times the exponential times k naught times the thickness times c sub I, our mode coefficients. And then in layer I plus 1, the eigenvector matrix times the mode coefficients. The exponential is gone because the local z coordinate is 0. And so we come away with two equations that are enforcing the boundary conditions at each interface on either side of layer I. Now the transfer matrix. We need to define the transfer matrix. Well, a convenient way to define it is a matrix that will let us calculate C sub I plus 1 directly from C sub I. So we would like an equation like this, where we take our mode coefficients in layer I, multiply by the transfer matrix of layer I, and get the mode coefficients in the next layer. So that's how we'll define our transfer matrix. Well, let's remember the equation we got from our second boundary. What we can do is we can solve this for c sub I plus 1, and we get this expression. Compare this equation to our definition of a transfer matrix. What that shows us is all this business going on here, this is the transfer matrix for the ith layer. And so that's how we calculate it. Let's talk about the stability of these transfer matrices. So here we are looking at this embedded layer, layer sub I, and of course there's a layer I minus 1 before that and an I plus 1 after that. Let's think about the waves. So we're calculating the z component of our wave vector in an embedded layer from the dispersion relation. That's the square root of the difference of two things. Our medium could be lossy. We could end up getting a negative number in the square root. So in general, these wave vector components are complex. The real part says that our field can oscillate. The imaginary part says our fields can decay. And of course, if we have both, we can see both. And that's what we're illustrating in this picture here. So we have a forward wave that's oscillating and decaying. Well, we know that there's scattering going on, right? So we're going to get backward waves, and they're still waves. So they still have a real and imaginary part of their wave vector. So those two can oscillate or decay. They just oscillate and decay in the reverse direction. But here's the thing. The transfer matrix method has combined forward and backward waves all into one big solution. So in terms of signs, we're really treating everything as if it's traveling forward. So we have to ask ourselves, what happens to this wave vector for backward waves when we're treating it, at least in terms of signs, that is propagating forward? What happens? Well, it turns out if it's decaying going backwards, but we treat it as going forward, we're essentially reversing the sign of our k's, which means this is an exploding exponential. And that is the origin of the instability for transfer matrices. The pure transfer matrix method is not stable. Transfer matrices do not work. Now there's fixes to this, but those fixes always involve sort of leaving transfer matrices, doing some stuff, and then coming back to them. But just the pure, straightforward transfer matrix method, as we have presented, is not stable, and now you know why. So how do we fix this? Well, if it deals with just treating backward waves incorrectly, obviously we're going to have to somehow distinguish between the forward and backward propagating waves. How do we do that? And there's a few ways, but here's one way. We can look at the z component of the Poynting vector. We can look at the cross product of E cross H. We do a whole bunch of work and we get to this expression. And we can look at the sign of the z component. If it's positive, we're talking about a wave going in the positive z direction. If it's negative, the wave is traveling in the negative z direction. So over on the right here, we're looking at our eigenvector matrix. And we can do this math, and we can identify which of those modes are forward propagating and which are backward propagating. Now what we see is that they're scrambled. So here we are again, and we've shown that these forward and backward propagating modes are scrambled. We've highlighted them. What we're going to do now is rearrange the order of the modes. We're going to do this in a way that puts all the forward propagating modes first and the backward propagating modes second. Now notice when I'm exchanging columns of the matrices, I can just do that for the eigenvector matrix, no problem, but I can't just swap columns in the eigenvalue matrix, right? I need these elements going along the diagonal. So I'm really talking about swapping these along just the center diagonal positions. Another thing we noticed, we could have looked at the sign of the eigenvalues to distinguish between forward and backward propagating. However you do it, we just have to distinguish between forward and backward propagating and reorder the modes so that we put the forward propagating on the left and the backward propagating on the right. Let's look at our matrices and see what has happened. After we have reordered it, we've essentially partitioned our matrices. And we can look at the quadrants of these matrices and ascribe physical meaning. If we look at the upper left quadrant, these are the eigenvectors associated with the electric field traveling in the positive direction. The quadrant in the upper right, that's the eigenvectors for the electric fields traveling in the minus direction, the backward direction. And likewise, the lower left is the eigenvectors for the magnetic fields that are forward propagating, and the lower right is the eigenvectors of the magnetic field that are backward propagating. We can do the same thing in the eigenvalue matrix. Of course, the lower left and upper right quadrants are zero, so we don't have to be concerned about them. But the upper left quadrant is our exponential for the forward waves, and our lower right is our exponential for the backward waves. So by sorting it, we can then partition our matrices and ascribe meaning to them. Let's look at a revised solution to our differential equation. So we started with a matrix differential equation, and we arrived at this solution. We then take our eigenvector and eigenvalue matrices, we do our mode sorting, and we end up in this form. This lets us do something else sort of interesting. What was just a single mode coefficient, we can now identify mode coefficients for the forward and backward waves separately. So we now have two mode coefficients. Our original mode coefficients is both of these in a single column vector, but we identify the partitions and we can separate mode coefficients for forward waves and mode coefficients for backward waves.
From the bottom of my heart, thank you very much for watching this video. I love hearing your stories about how these videos helped you. I also love answering your questions. So please tell me your stories and ask your questions in the comment section. I promise I will try to answer every single question that's asked. If you like this video, hit the like and subscribe button. I also recommend visiting the official course website that has links to the latest versions of the notes, the latest videos, and there's lots of other resources to help you learn, including implementations in MATLAB. I'll see you in the next video.